Hello everyone, it's great to be here today to learn together about a new technique. Today, we're introducing polarimetry, which is a technique used to measure optical activity and analyze chiral molecules. It is based on the phenomenon of light polarization and involves measuring the changes in the polarization state of light to determine the content and properties of chiral molecules in a sample. Let's begin by introducing the principles of this technique. First, I'd like to ask you if you remember what chirality means. Chirality refers to the asymmetric nature of molecules or objects, which they do not overlap with their mirror images. Chiral molecules exist in two forms, known as enantiomers or mirror images, which are mirror images of each other in space but cannot be superimposed by rotation or translation. These two forms of molecules are called the left-handed L and right-handed D forms and can also be represented by the Latin letters R and S. While we are familiar with the differences between R and S, do you know how to distinguish between them? If you have a solution containing only R or S or a mixture of R and S, how would you determine if the solution is pure or mixed? One method of distinguishing them is by determining how they rotate plane polarized light in any direction. And this is where we introduce polarimetry. Polarimetry is the technique we use to measure optical activity. The actual device used is called a polarimeter, and if you look closely at the word, you'll notice that polar is related to light, and meter is related to measurement. Light is how we measure the optical activity of chiral molecules. Firstly, we generate a light using a light source, which can be white light or monochromatic light. Now, I'd like you to recall some of your knowledge about light. We all know that light can exist as particles or waves. If we consider it as waves, light oscillates on a plane perpendicular to its direction of propagation. This plane is called the plane of polarization. The direction of this oscillation can be in any direction. To ensure that light oscillates in the desired direction, we simply need a filter with a small slit. When light is incident on the filter in various orientations, only the light oscillating in the up and down direction, which is allowed to pass through the filter, can continue to propagate. The polarizer in the polarimeter serves this purpose. Now, the light oscillates in the desired direction. As it passes through the sample, the light encounters the substance, which causes the light to change its direction. We can observe this change clearly. Both R and S chiral molecules have the ability to rotate light in a specific direction. However, the direction in which light is rotated depends on the substance. For example, R2-butanol is different from R-ethanol, and R2-butanol is different from S2-butanol. Each has its own unique characteristics of rotating light. As light encounters more and more of the substance, the rotation angle continues to change. The light, now with a changed polarization direction, enters the detector, which is made using a photoiode or a photomultiplier tube. The light signal is converted into an electrical signal. The electrical signal then undergoes analysis and recording through a data processing system. The data processing system can measure the optical rotation angle, which is the angle of deviation of the light caused by the polarimeter. The rotation angle is equal to the concentration of the sample multiplied by the length of the sample tube multiplied by a known proportionality constant. By comparing it with a standard reference substance, the content and types of chiral molecules in the sample can be inferred. How can we apply this technique in clinical settings? Polarimetry has various applications in clinical practice. Here are some common areas of application. 1 is drug analysis. Polarimetry can be used to measure the chiral purity of drugs. 2 is disease diagnosis. For example, in the field of ophthalmology, polarimetry can be used to measure corneal rotation in the eye, aiding in the diagnosis and monitoring of corneal diseases such as keratoconus. 3. Diabetes management. Polarimetry can be employed to measure blood glucose levels, assisting in the management of diabetes. 4 is protein structure studies. Polarimetry is used to investigate the chiral properties and structures of proteins, revealing their functions and mechanisms of interaction. As an optical detection method, polarimetry has the following characteristics and advantages. 1. Non-destructive measurement. Polarimetry is a non-destructive measurement technique, making it particularly useful for studying fragile or limited supply samples. 2. Is high sensitivity. It can detect very small changes in the angle of rotation, making it highly effective in measuring low concentrations of chiral molecules or for trace analysis. 3. Is quantitative analysis. It allows for the accurate determination of the content of chiral molecules in a sample by comparing it with a standard reference substance. 4. Rapid measurement. This is particularly important for clinical diagnosis in laboratory research that require efficient analysis. Well, that's the principle of polarimetry. In our next videos, we will continue to explore the applications of polarimetry in detail. Stay tuned and keep following our video series. Thanks for watching.